Our project is effective learning from demonstrations using causal graphs. We proposed a series of methods to gain causal knowledge and experimented it with multiple RL environments to test its effectiveness. Next slide, please. Our project roots from the classical RL task behavioral cloning. It reduces policy learning to supervised learning to predict expert actions given observations. However, such models are usually non-causal, meaning that the training procedure is unaware of the causal structure of the interactions between the expert and the environment. Next slide, please. The distributional shifts in imitation learning can lead to causal confusion, where spurious correlates are mistaken to be the causes of expert actions. Practically, it means that access to more information can yield worse performance. Next slide, please. Then how can we circumvent causal confusion? To study this problem, we performed some literature review and implemented the causal confusion paper by hand as our baselines. In the mountain car environment, we use the pre-trained agent to generate demonstrations of different sizes. Next slide, please. We do observe causal confusion, although the action should only be dependent on original inputs, which is the current positions. We added previous actions and previous positions as confounding variables. You can see that the confounded model can still have similar training loss, but the testing loss can be significantly higher. We also tried the, next slide please, the intervention strategy mentioned in the same paper, namely intervention by policy execution. However, we observed this method does not have wide applicability because of the brute force nature of posterior sampling it uses. It is hard to implement it in higher dimensional problem. Also, interpreting the confounded causal graph is non-trivial at all. It still requires some expert knowledge. It's more or less a chicken and egg paradox. If human experts already know what should be the real cause, why bother doing the intervention? So we try to find other better autonomous ways to connect learned causal graph to RL agent. Yingqi?
So for the methodology part, the goal is to use causal knowledge to utilize the expert demonstration data. We have two tasks here. First one is to infer the action effect, basically estimate the reward given the action intervention and the state. And the second task is to learn the policy pi that minimize the difference between itself and expert policy pi d. To do this, we basically use the causal discovery techniques to remove spurious correlations. Next, please. And we use the PC algorithm, which is a constraint-based causal discovery algorithm to reduce the spurious correlations. It is based on the theorem that X and Y are adjacent if and only if they are dependent conditional on every subset of remaining variables. Next slide, please. So in the first step, we learn the skeleton, and to do that, we basically conduct a set of conditional independence tests. Basically, for each edge, we test variable x, y connected by that edge if they are independent condition on the subset Z of all neighbors of x and y. The CI tests are organized by levels, so based on their size of conditioning sets. At the first level, all pairs are tested conditioning on the empty side, and size of conditioning set D is progressively increased each iteration. Next, we do the orientation propagation. We first find the V structure and iteratively to check if there are more edges can be oriented. Next slide, please. So here we have the DAG, which have the nodes of state, action, and rewards. And we use the neural network to estimate the action effect and also the policy. Next slide. Next slide. So the overall structure of our algorithm is we basically have the states with confounders as input, and then we run PC algorithms to get the binary mask to remove all the confounders to get the cleaner states and pass it to the neural network to obtain the reward estimation and the policy. Next slide, please.
So we performed two sets of experiments with 3 variations each. The first environment was mountain car, and the second environment was cardboard. So as you can see in this mountain car, the car has to reach the goal. It has 3 kinds of actions and 2 kinds of states, which is the position and velocity, and it receives a reward of -1 until it reaches the goal, or it reaches 200 steps of the iteration. So we have two input options where we can pass the original state, the current state as it is, or add some confounders, which is the previous state plus the previous action. So the three variations are like the first one, we do imitation learning without confounders. Second one, we do it with the confounders. And the third one is similar to the second one, but the only difference is that we just add, instead of the previous action, we make it a randomized previous action. So as you can see, the algorithm, in this experiment, we collect all the data at one go using a trained PPO model and generating expert trajectories. And we train our behavior cloning on the whole model or the whole data set. Whereas at the next experiment, we gradually build our experiment. So as you can see, in this experiment, the new experiment with the cart pole, the cart has to maintain its balance. It has two kinds of actions and four kinds of state. And you can see the ending termination condition. So in this one, the output, we add another reward for the final case. And the three variations are like the first one, we do it without the co-founders. The second one, we do it with the co-founders. And the third one, we do it with a causal discovery structure where we update the mask of the co-founders, where we want, where which co-founders we want, we try to update that mask, as you can see the algorithm in the sixth step. Next.
So now let's talk about the results. So the first environment that we did, like we ran this behavior cloning method, was the mountain car one. And like following is the loss with the epochs. So like as the number of epochs like increase, we are training the model over and over again. So as we can see, like, the green one is the state input, where like we only have the current state as the input and we are trying to predict what action should be performed. And we see that actually the loss is the least in the case of the multiple inputs when we have the present state, the previous state, and the previous actions. However, like in our third test case where we have the previous action replaced with a randomized vector, in this case, you actually see that the performance decreases heavily. So why is this the case? Is because in the confounding inputs, which is with a multiple input test case, the the network actually learns a lot of different relationships with the previous actions which are not actually present. It might be because of the noise and other things, and it just like learns to repeat those actions. So like in the test case scenario, we see that the performance actually decreases, and this is an effect of like confounding inputs in the behavior data. Then we actually run like similar experiments in the cart pole environment. And this is actually the result of the trained model when we allow it to perform in a real environment and identify and like evaluate how much reward it can accumulate in the episode. So on the left hand side, we see that this is the training of with the previous action as the confounder, and the three test cases are the imitation confounded, and imitation causal. So the imitation is like the vanilla behavior cloning method where like we input the current state and we try to like learn what action needs to be performed. And the confounded one is where we have the confounded inputs, and the causal one is where we actually do the causal discovery algorithm first to identify the binary mask, to identify which states are important. And then we do behavior cloning after that. So we see here that, like it performs very similar to the imitation confounded result when the previous action is the confounder. However, when the previous action is actually replaced with a random set of actions, then we actually see that the imitation confounded actually performs worse in the like earlier part of the training. This might be because that, in like when the amount of data, like the size of the data set is small, like there are a lot of different relationships which the imitation like this algorithm gets confused with. But the imitation causal thing actually is able to identify the different relationships and is able to get rid of them. Then finally, we do the same training. However, in this case, we are training the imitation causal with reward prediction. So there's an additional loss that it needs to predict the reward along with the actions. And in this case, we see that the imitation causal actually performs much better than the other ones, like, especially in the earlier part of the process when the data set size is very small. So this is just the example of what the graphs look like, and there are less number of edges than a fully connected graph. So it identifies what states are not related to each other and hence does that. Similarly for the cart pole and the mountain car experiment. Finally, coming to the takeaways, with the confounding variates are present in high dimensional behavioral data. So this is an important method to identify those covariates and to like remove them from the training methodology. Then our method can result in efficient learning with very limited expert data, as shown in the results. The iteratively running causal discovery algorithm can help us remove the correlations in expert data. And finally, like some of the limitations is that the PC algorithm is actually exponential with the number of nodes. So like as we increase the like state size, that is we use high dimensional data or we use like image based data, the runtime would actually increase exponentially. So that might not be like much preferable. With that, we'd like to thank like end our presentation. Thank you.